You see the screen?
Yes.
Perfect. So good morning again. And this talk is a continuation of yesterday's talk, and it aims to answer how can you effectively use C++ inside of JEDI? And for this half of the talk, I'm going to talk about containers in the C++ standard template library, and then math inside of what's called the eigen library. And then I'm going to just go through a couple of examples of best practices when writing computer code. So I know that I haven't gone into the concept of templates into too much depth besides saying that they exist and what they look like, but I do want to tie them into a very important feature of C++, and that is its library support. So with libraries of code, you can reuse something that another person wrote very easily. And both the standard template library and eigen are widely available and very well documented. And because they are so common, again, people can readily understand what you yourself have written. And we really use these both extensively inside of JEDI, so they're just worth going through. So C++'s standard library is called the standard template library, and I'll explain what that means and show many examples. But basically, this STL, as it's abbreviated, is built into every C++ compiler, so you always have it available. It is a very large library, and the majority of functions and classes are actually built in templates in some way or another. So you can find containers of objects implemented with templates. You have algorithms that are also template based. And then even the input output for, say, your console is also template based. Same with strings, because you can have different potential types of strings, say with different character widths or different character sets. If you want to explore these further, I do recommend the links inside the slide. So every part of the standard template library is very well documented on these slides. So there are examples for every single function and class. And all the links here point off to c++.com, which is a very useful reference. Since these sites provide so much documentation, I am not going to talk about all of these. And instead, I do want to focus our time on containers and strings because these are the bread and butter of a lot of what we do inside of JEDI, though I will briefly touch on some of the others. So first, containers, because they are very useful. So containers are objects that contain other objects. And when I say contain, I mean that these containers manage their own sets or groups of objects inside. And when I say group of objects, I mean things like a series of integers or floating point numbers or C++ classes, strings, or complex numbers, basically whatever you can think of or express inside of the language. So you can insert objects into the containers, you can list the objects inside, you can take them out, you can dynamically resize all of these, and so on. All of the objects inside of a container share their lifetime with the container too. So that means that the container owns these objects. When the container destructs or goes out of scope or just goes away, all the objects inside are also destroyed. I'm going to show 3 containers here, but the standard template library has many others like stacks or decks or bidirectional lists, and each of these is useful under different circumstances. There really is no one-size-fits-all approach, but these 3 are some reasonable default choices. So the first one is a vector, and a vector holds a contiguous sequence of objects. In the case of a vector of integers, we're storing a contiguous sequence of integers. And you might ask, well, why would you use this? And this is because a standard vector is a lot better than a C style array or a Fortran style array because it is fully resizable. You can basically store data of any arbitrary size. Now, the definition to the right of the page is a bit verbose, so I'll just go through a couple of examples to show you what you can do. So let's just start with going through this example block of code so that you can read it. So to start, all vectors are inside the vector header. And we're also going to be writing data out to the console, so we include the IO stream header. So again, these are part of every C++ distribution. then here's one way to make a vector of integers. We say standard vector, it's containing integers, so that's the template parameter. We just give it a name, v, and then we set its initial data. So it has these four numbers, 7, 5, 16, and 8. Then we call a function called pushback, which just appends elements to the end of our vector. So it's dynamically resizing our vector and adding in new data. And then right here, we have this little loop, and this is what's called a range-based for loop. It's basically for all integers, we call those n, inside of our vector. We loop over each one and we print it out to the console. So then you get something like this. So again, it's a very basic interface with a lot of power. So you have a smart resizable array at your fingertips. In a vector, any element can also be accessed in constant time. And that means that whether you want to access the first element in a vector in C++, just like in C, indices start at 0, or the 1000th, or the first, or the 5000th, the time needed to access that element is about the same. And for much of what we do in JEDI, we are accessing arrays to perform math, or we're just iterating over elements. So this constant time access is very useful to us. So there are multiple ways to access the elements of a vector. So the first one is using indices. The first element of a vector, or the 0th element, in this case is a 2. The one after that is a 4, then a 6, then an 8. We also, again, have this type of range-based iterator that you have where you can also just say, start at the beginning of the vector, go to the end, and iterate over every possible value. To the right, I'm just going to show an example of the resize function, and this is what you can use to manually change the size of a vector instead of sticking data into or out of it. Sometimes you might want to truncate it or expand it and fill it in with zeros. And you can accomplish that using the resize function. Now, the maximum size of any vector is limited only by your system's memory. Vectors do need a contiguous block of memory, though, in which to store their data. So if you try and expand a vector, that expansion can be very slow because your system might have to copy the data to a new place. So you should always consider the size of your data before you start appending new elements to it. But that's just generally good programming anyways. Conversely, shrinking a vector is always a very fast operation. You're just chopping off stuff at the end and forgetting about it. So this example on the slide just gives you another method of iterating. So again, another exposure. And in this case, we have vectors of more than just integers. You can have vectors of strings, or you can just have vectors of individual characters. Again, it's a templated class, so it can contain anything. So in this case, we're iterating in a slightly different way. Auto, by the way, is a C++ keyword used to tell the compiler that it can figure out what type of object this iterator, which I'm calling it, is going to be, because the return value of this function is going to be a specific type, so the compiler just automatically knows that. So it's a nice shorthand. But anyways, this is a third type of iterator because all of the standard containers provide functions called begin and end, or cbegin and cend, rbegin and rend. Each one of those is slightly different, but they provide what's called an iterator, where you can iterate over an object or a part of an object in either the forward or reverse direction. So in this example, we are iterating over all of the integers and we're just summing them up together. And then we print out the sum. In this case, we're accessing the first element of this vector of strings. And this asterisk here is an operator. So we're accessing the value of what the iterator is pointing to. If you know about pointers, then that might make some sense. If not, just assume that it's part of the language and that you need that asterisk. But then we're just accessing the first element and we print it out. Finally, if the beginning of a vector equals its ending, then that generally means that its size is empty with how C++ counts things. There's even a special empty function inside of vectors that you can also consult. Now, you can also append elements using the pushback function, which I mentioned earlier. So we can just attach data to the end. So we can append strings to strings. There's also an insert function, but if you want to insert lots of data at arbitrary places, then a vector might not be the right tool because the performance might suffer a bit. To the right, just one more example, there's a function called clear, which erases an entire vector. So in this case, we set some data, we decided we want to dump it all, and then we want to replace it with something else. There's a lot of available functions, and the real takeaway is that if you want to write or understand C++, this is one of the essential classes that you should become familiar with. Now, a vector isn't the only type of container that you might encounter. We also extensively use what's called a map and another container called a set. So think of a map as like an index or a cross-reference that you can search through to get some other related data. It's basically a set of key value pairs. A set is a simplification of this. So instead of keys and values, you just have the keys. And you might wonder why we want to use these also. And that's because they have different performance characteristics. And again, for a map especially, you can establish a one-to-one relationship or sometimes a one-to-many relationship between objects. But for the performance, sets and maps are slower to build than vectors. So adding in elements when you first construct them is a bit slower, but then adding in arbitrary elements is faster at arbitrary locations. Here's how you can sort of read this table. This is the container that you're using. And then say that you want to, say, search for a specific value inside of your container. With our map or a set, this is a lot faster than it is for a vector. With a vector, you have to start at the first element and work your way all the way through manually, and that's very slow. Whereas map and a set implement what's called a balanced tree. So if you're trying to look up something like in a dictionary, it goes much faster again. So again, with these different performance characteristics, some of these containers might be more suitable for your uses than others, but it always depends on the problem. So that's enough for containers. I'm also going to briefly touch on strings because strings are exceedingly useful. We use strings to store satellite names. We use them to store dates and times for right now. We use them to store station IDs. And really, a string has any set of characters that you can manipulate. And a string in C++ is another object. C and Fortran don't really have strings as independent objects. They just have pure character arrays. So the C++ string manipulation facilities are a lot more powerful. So just like with a vector, you can add strings, you can compare strings, you can manipulate them in a whole variety of ways. And most of the functions that are built in are built directly into the string class. So I'm just showing you a few of the very common ones. And here's an example to the right again of how you can manipulate a set of strings. So in this case, here's just a mini program. Strings are all found inside of the string header. And then we can just define a string saying like this is an example. Then we're calling a function available called operator append. It's very similar to this one. And we're just appending to the string. So after here, we would have a string saying this is an example used in the JEDI Academy. Then we call an insert function to insert some text at a certain location. So then we have this is an example used on day 4 in the JEDI Academy, but that's not grammatically correct. So we just have another replace, and then we get this at the very end. So again, you can do a lot with strings, and unlike with C, you don't have to manually resize strings or pack them differently. And unlike with Fortran, these strings don't have a fixed width. Besides for strings and containers, I also want to briefly mention the standard algorithms that are part of the template library. And these encapsulate many of the common tasks that you want to do just in your day-to-day work, and they make your code a lot easier to read. So there are hundreds of different ways to write a sorting function or a copy function or a function to find the maximum value in a whole set of numbers. And really, rather than having you reinvent the wheel over and over again and having your own readers of your code parse very complicated loops that you might come up with, I'd say that it's a lot better to express your intent very clearly. So here's what I mean by that. Here's a bad example taken from the C++ core guidelines document, and I had a link to that on yesterday's slides. And this is somebody's attempt at replicating the basic standard find function, which what it would do is it would search for a value in a sequence and just tell you where it found that value. So it's just returning an index location. Now this version needed user interaction to manually specify what you were looking for. It's got a handwritten search loop that's a bit verbose, And it also has a couple of hidden bugs. And if you explore C++ a lot more, you can eventually start to see some of these bugs. But again, it doesn't occur when you're just glancing through the code that this code might be buggy. So it's a lot clearer to just use the function that's available from the standard. And in this case, you now have clarity of intent. You are separating out your logic for first reading in the value that you're looking for, and then separating out the find feature. And then now it's a one-liner, so anyone can actually understand what you're doing. So Maryam is going to give a talk later today about code review and pull requests and unit tests. And really, we have to do a lot of code review for JEDI because we have many contributors. And it's a lot easier for everyone involved if we make the code simpler. Now, for interest of time, I'm not going to go into details on pointers. These are another feature of the C language, and they provide the really cool ability to reference memory by address instead of copying data by values all over. Fortran implicitly uses these in function calls because everything is passed by reference, which is a type of pointer. And I will really recommend looking at a tutorial for these, and you'll probably have to think about them a lot for quite a while before you understand how they work. In JEDI, however, we use a couple of tools provided by the standard library again for wrapping pointers and for making sure that the memory that they point to is properly taken care of when it's no longer needed. So in this case, if you're looking at the JEDI code, you might see references to a unique pointer or a standard shared pointer or to a weak pointer. And these are what we use to wrap these raw pointers from C. And we use these a lot inside of the factories that we use to produce objects because we have what's called object inheritance, and we return pointers to an object that we then wrap up. So a pointer is like a container with one element, and each one of these pointer objects has its own unique characteristics. For a unique pointer, you can only have one copy of the pointer itself. For a shared pointer, a whole bunch of shared pointers can share ownership of the value that they're pointing to. And then once the last one is destroyed, then it takes care of any cleanup tasks. So really, in general, you won't need to use pointers directly, but again, you might encounter them inside of JEDI. So it's just useful to see it or be aware of it. Now, that's the majority of what you will most commonly see inside of JEDI that's related to the standard template library. But we do use a couple of other libraries. And one of these is the eigen library. And I'd like to talk to you about this for a little bit too. So the standard template library is very useful for a lot of cases, but it is less than ideal when you want to store multidimensional data or when you perhaps want to do math on arrays and matrices in C++. And here's where eigen really shines. And what eigen is it provides really fast math operations that are easy for a human to understand and are really easy for a compiler to optimize. So by that, I mean the code that eigen writes is faster than the code that you will be able to write. It's also faster than the code that I will be able to write and most of the JEDI core team because specialists have gone in and they've optimized it very thoroughly. So this was originally designed as a library for fast operations on matrices to do things like singular value decompositions or LU decompositions or Fourier transforms and the like. And we use it in a whole bunch of different places, and we're trying to use it more inside of YODA and UFO. So the big reason that we're using it again is that it's a specialist library and that C++ and C are very limited with how they can handle multidimensional data. So this particularly matters for cases where we have a lot of brightness temperature channels or where we have very large matrices. You probably will see eigen for any type of manipulation of that. So here's the fundamental example of how to make an eigen object. So I can go through this and explain it to you too. So off to the right, we have a little bit of CMake code. So if you wanted to compile this example independently, you would have a cmakeless.txt file that looks like this, and it tells CMake to find the eigen package and build this program. And here's what the source code would be. So a lot of eigen is found in the eigen/dense header that the eigen package provides. And there's this one object called an eigenarray. And this object is just a generic two-dimensional array for handling double precision floats. So in this example, we make a 2x2 array, then we set some basic coefficients, and then we print it. So this one doesn't do very much, but it just gives you an idea of how you would create an eigenobject. Now you might ask, okay, what is this actual object? And just like with all the standard template library stuff, this is also a template. So this is basically a shorthand that expands to this. This is an eigenarray that stores double precision floating points. That is a dynamically sized object where you can resize it so it has an arbitrary number of rows and columns. And it is storing your data in column major form because column major versus row major data is more suitable for CPUs. Apologies here, I meant to click through these. So for the storage type, you can pass in other types of data. You can have an eigenarray of floats or characters or of integers. You can specify fixed dimensions to your arrays also, but you usually don't have to. And for the row versus column major example, say that you have a 2x2 array of just increasing integers. With row major storage, which is what C uses, system memory has all the data stored in order of, say, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it goes along inside of rows. For column major storage format, that's what Fortran uses. It goes down in columns and it maps the data out linearly like this. And it turns out for actual numerical processing, column major is a little bit faster with how modern CPUs are implemented. Anyways, that might be a little bit too much detail for you guys, but basically this very expressive template can perform coefficient-wise math inside of what's called eigenarrays, or if you're using a similar object called an eigenmatrix, you can do matrix-wise mathematics. So here's another example where you have two 2x2 arrays and we just feed in some initial data. And then due to the power of C++ with templates and also operator overloading, you can define another array, C equals A plus B. You no longer have to hand write out a loop to go row by row and column by column to add in the numbers, which is really cool. You can even do more complicated statements involving multiplication or raising arrays to different powers or multiplying them repeatedly or subtracting them or adding on individual coefficients. So again, we are turning the science problem back into science instead of having to have a scientist translate the operations that they want to do into something that would be more computer readable. We are trying to keep the readability for everyone, and we're trying to keep the performance. Just a few other things that you can do with eigenobjects are listed on this slide. So you can resize arrays. You can cast arrays from one type, like a double precision, to an integer or to a float. You can do block operations on arrays too. So say that you have a very big multidimensional array, you can select a subset of that array with the block function. Here's an example of applying it. There's, say, set constant, where you can set all of your array to a constant 0. Or you can select a certain block and just set that to a constant. Again, you can do a lot of stuff. And I have a link on this slide that's provided for everyone. And this links you to the very first tutorial on the Eigen website. And they have a series of 9 or so tutorials that show off the basic functionality of the library, and then they slowly add on new features. And there's really a lot that you can accomplish here. So in JEDI also, we use several other libraries, and here are a couple of them that you might encounter if you go through the code again. So I'm not going to talk about these, but if you do see them, know that Atlas usually involves meshes. ECKit provides parsing of YAML, and it provides some of our MPI task distribution and quite a few other functions. FCKit is the library that we're using to bind Fortran and C++ code together. because there are a lot of issues there too, because Fortran and C++ are very different languages. Then there's the Boost library, which adds on a whole bunch of different possible features, and we're using it for deterministic pseudo-random number generation and a few other things. And recently to Sabre, we might be adding on the Seagull library, which is a computational geometry library, which provides very efficient mesh-based data structures. So again, this is exceedingly useful for interpolation or regridding of data. Now, I know that I've dumped a lot of information on you guys, and this is because C++ is very big, and a very thorough introduction would take, say, a whole semester at a college. But to close, I'm just going to mention a few more best practices to keep you from pulling your hair out in frustration. And this really is not an exhaustive list, but it's merely what we see frequently as members of the core team for JEDI. So just keep these in mind whenever you write any computer code, and not just with C++. So the first idea is to automatically assume that somebody else will get confused when reading your code. And you as readers probably will be confused by other people's code as well. So you should really always aim to make code as simple as possible, and you should try and make things as simple for people as possible. You should document your code thoroughly. You should use very descriptive names. You should have functions that perform very easy to understand functions and don't have weird side effects. So here's an elaboration on this idea to show you a couple of cases where this applies. So this is defensive programming. So say that you had a function just inside of an engineering library called change speed, and then you just pass in some double. But as a reader, you might be confused, wondering, like, what does this double actually signify? Are you changing your speed in kilometers per hour or meters per second or miles an hour? So again, it's helpful to add in the units. Another question that you might ask is, are you changing to an absolute speed, or are you changing via a delta or a relative speed? Are you just increasing speed by 10, or are you setting your speed to 10 meters a second? So again, apologies if you can hear the dog barking in the background, but again, the idea is to be very explicit, and not just to make sure that you can understand C++, but if you want to write any, you should try and make it so simple that everybody else can't misunderstand it. So there are a couple of corollaries again. So the first one of these is to use comments and document everything that you write, because this helps people to understand what you wrote later on. So here's an example of some of the documentation that we have inside of JEDI, and this is documentation for one of the classes inside of Yoda. So this is a specific coding format, and we use a tool called Doxygen that reads in this special format of comments, and it makes web pages and PDF manuals. So instead of people having to pour through a whole bunch of source code, they can just visit a website and click on a whole bunch of different links. So Doxygen is used ideally to document every function and variable that we are using inside of JEDI in every class and every namespace and hopefully every file. This is a moving target, and we use it again to generate a website. And it's also very helpful because it can make diagrams of flow in our code. We can say, okay, this one function calls these other functions. And then we just click a link and we can see, okay, these other functions call these other functions further. And then we can see how everything fits together more easily. So if you're writing anything too, you should probably write with this in mind so that people can follow the logic of what you've created. So the second corollary, keep all of your functions very simple. Don't produce, say, one of those old Fortran-like functions that goes on for 1,000 or 8,000 lines with 100 variables, all with very bad names like A, B, C, and D. Nobody can understand that in the future. So if you see something that's very large, or if you've written something that's very large, try and break it up into small, easily testable components. Now, Miriam later today is going to give a talk on unit testing, which is how we validate that our code behaves the way that we think it does. And this, again, is very useful, especially when you have small functions, because then you have fewer code branches to keep in mind, and you have fewer cases where you can hit undefined or unintended behavior. And then also, if you're ever writing code that somebody else will read and they're actually reviewing your code, break up really large pull requests or requests for changes into small manageable fragments so that people can understand it. So Yannick talked about agile development, and this is the essence of agile development. 2 or 3 more bits of advice. When you are building any new code, turn on the compiler warnings. So in GCC, you can pass in an option called warn all. And this is a very useful option because the compiler understands C++ better than you generally do, or it understands the structure of the language better than anybody because it's building the code. And you might have written something that is a bit undefined or out of bounds for the regular language, and it's basically warning you about a potential mistake. It's not an actual error, but it might be an error from the standpoint of the program doesn't perform as you expect it would. So we've actually got an automated internal system called C-, and this figure here is from that. And I just did a sample build several months ago, say back in like last year, January, of a bunch of different JEDI projects. And then we could go through every project and we tried to play the whack-a-mole game of removing every warning that we could find. And we actually did fix all of these. But again, it's useful for illustrative purposes because we do want to try and track this and reduce the number of possible warnings as we develop the code, because we want high quality JEDI software. One other thing, you should always test your assumptions right defensively. So if you're trying to do things like adding 2 vectors of data, first, before you add them together, make sure that the vectors have the same size. If you're reading any user input, make sure that it makes sense before you try and run based on that input. We had a couple of questions yesterday where people asked, okay, during the practical, my program was failing because something was wrong with the YAML, but we couldn't figure out what. That could have been a little bit of a shortcoming where the parser didn't validate the input before trying to run on it. And if the parser had realized, hey, something seems very wrong at the very beginning, it could have then passed in a message to help people diagnose. So also, if you're writing a multi-step program, you should really check to see if a step has failed before going on to the next task. Again, just like with driving, drive defensively and program defensively. And there's really no easy solution to having a machine automate this for everybody. People, whenever you contribute new software, always have to program in a lot of these checks yourself. We do, however, have a policy where we try and review new code that comes into JEDI, and we want to have at least 2 separate eyes on it to make sure that the code looks at least okay. And this is one of the real ways where you can learn C++ too, and that's through practice. And in JEDI, if C++ feels a bit too much, we also do write some Fortran codes. So if you do have access to our internal repositories, we welcome and solicit reviews all the time. If you don't have access, again, C++ and Fortran and science is found everywhere. And in particular, NOAA EMC nowadays has switched to open development for a lot of their models. And several of you might be working on that. Or you can try doing this in many other JEDI-related projects. Anyways, I hope that this talk has helped you to understand C++ a bit better, if not in practice, then at least in theory. And I hope that you can apply this to understanding JEDI or really whatever software you find yourself working on. So let me just say thank you for your attention and ask if you have any questions.